As an overview of the properties of our rational functions, what we're doing is we're taking a polynomial function divided by another polynomial function. And when we do that, what often comes through are vertical asymptotes and horizontal asymptotes. When we have even powers, so like 1 over x squared, 1 over x to the fourth, 1 over x to the sixth, our functions look like this. And where we have vertical asymptote at 0, horizontal asymptote at 0, and everything's positive. When we have odd powers, so like 1 over x cubed, x to the fifth, x to the seventh, we have those same vertical and horizontal asymptotes. It's just when x is negative, y is also negative, and when x is positive, y is also positive. So let's talk about kind of these transformations where this original function, what I'm seeing is a 1 over x, but then next to x I have a plus 2, so that tells me that we're going to be moving to the left 2 units. And what I'm going to do is, typically with 1 over x, we have those vertical and horizontal asymptotes at the y equals 0 and x equals 0. We're going to move those to the left 2, which horizontal asymptote isn't going to change. So that's going to stay the same, but our vertical asymptote that's usually at 0, we're going to move that to the left 2 units, like that. And then from there, what I'm going to do is just pick up, and it's kind of like when we have our odd powers, what I would do is I'd usually have like the coordinate 1, 1, move that over to the left 2. And then if I have at 2, I would usually have 1/2, but now that would be moved over 2 units. And then I also use the one where if I had 1, I would have a when I have x equals 1/2, I would have an output of positive 2. I'm also going to use that one. And then from there, that just gives me something to kind of show the curvature, but then everything else is just bounded by those asymptotes. And then I would have the same things over here. So I'd use that 1/2 and that 2 to kind of get that structure going. And then we're stuck with those asymptotes. Okay, with this one, so what I'm noticing here is I have that x squared. So I'm going to be thinking of my original function as 1 over x squared. However, what we're going to have is a shift to the right 3 and down 2. So again, I'm just going to focus on the asymptote. So where I would have the asymptote, let's say the horizontal one at 0, that's moving down 2, where I'd be at x equals 0, the vertical asymptote at 0, we're moving that to the right 3 units. Sorry, stumbling on my words here. Okay, so 1 over x squared typically looks like this, where we're all above the x-axis. However, now we're all above that horizontal asymptote at -2. So I'd have my 1, 1, I'd have 2, 2, or actually, sorry, it would be squaring it. So where I would usually have 2, now I'd have 4. And then where I'd have 1/2, I would have a 4th. And then same thing over here, 1, and then where I'd usually have 2, I would have a 4th because of the squaring, and a 4th, and that's enough to just get a general graph going for our function with the transformations. Okay, so let's talk about how to find those horizontal asymptotes. And what it's going to come down to is comparing the degree of the numerator and the degree, which we're going to call n, of the denominator. So we're basically comparing exponents of the two. If the degree in the numerator is smaller than the denominator, our horizontal asymptote is just y equals 0. If the degrees are the same, then we end up, let's change that a little bit. So let's use an example here. Let's say I have a function that is 3x cubed over 2x cubed, and let's add some more things there so it doesn't just cancel out. Okay, so the degree of the numerator and degree of the denominator are the same. What we end up doing is, for our horizontal asymptote, we use a ratio of the leading coefficients. The leading coefficients are attached to where we got our degree from, but it's the two numerical values. So what I would do is create a ratio of that 3 divided by 2 for this example. So if I want to find the horizontal asymptote, I look at those leading terms and grab those leading coefficients and divide them. Now these last two cases, we're not going to worry too much about. Either the horizontal asymptote doesn't exist or we have an oblique asymptote, but we're not going to worry about finding the oblique asymptotes for now. Okay, so let's look at our scenarios here. So what I'm going to do is, in fact, I'm just going to go across all of these and comparing numerator and denominator. I'm going to find my leading terms, which these are nicely organized, but really I'm just looking for where I have the highest exponent in both the numerator and the denominator. Okay. So for this first scenario, in the numerator we have a degree of 1, in the denominator we have a degree of 2. Now because the numerator is larger, our horizontal asymptote is just y equals 0. Nothing else to do there. That's our horizontal asymptote. With this one, degree of the numerator is 2, degree of the denominator is 2. So because they're the same, our horizontal asymptote is going to be a ratio, and we're going to take those leading coefficients. So 5 and 10. So this has a horizontal asymptote at 1/2. Degree of 3, degree of 2, and with this one, our numerator is larger. I realize I just wrote that backwards up there, sorry. The 2 is larger. Okay, when the numerator is larger than the denominator, then what we're going to say is either no horizontal asymptote or oblique. In this case, it's exactly one more. This would result in an oblique asymptote, and we'll just leave it at that. This one, we have 4 and 2, where the numerator is larger and it's larger than more than 1. So we're just going to say no horizontal asymptote. Okay. Then our very last thing here is the short run behavior. So that comes in the form of the vertical asymptote, the zeros of the graph, and whether or not a hole occurs. And where holes will occur is if we factor our numerator and denominator and there's some sort of cancellation. Where that cancellation is occurring, there's a hole right there. So let's look at some examples here, and we'll also look at the graphs in Desmos as well, since that can help too. But where we'll start is, let's go ahead and factor the numerator and denominator. So the numerator, that looks like it'll be an x minus 6 and an x plus 1. And the denominator will have an x plus 4, x minus 3. So if I want the zeros of the graph, this is the equivalent of just looking at the numerator and setting it equal to 0. So that factored form will help because we'll have x minus 6 is equal to 0, so we'll have an x equals positive 6. X plus 1 is equal to 0, so x gives us a negative 1. So we have 2 zeros of our graph coming through here. In fact, let's write them in coordinate form in case we needed to graph them, and we'll be all set there. In terms of holes in the graph, nothing canceled out between the numerator and denominator, so there are none. Which do we want to start with? What order did I write? Vertical asymptote. We're focusing on where does the denominator equal 0? Because we do not want a denominator of 0, so that's where the vertical asymptotes will pop up. So we'll have where x plus 4 equals 0. So at the line x equals negative 4 is one vertical asymptote. And then where x minus 3 equals 0, which is an x equals positive 3, also a vertical asymptote. And then our last piece is horizontal asymptote. And with that, I'll compare the degrees. So we'll have degree of 2, degree of 2. And because those are the same, y will be a ratio of the leading coefficient in the numerator, leading coefficient in the denominator, which is just 1 and 1. So 1 divided by 1 will give us a horizontal asymptote at 1. Let's check out the graph and see how all of this shows up there. So I'm going to go to the Desmos graphing calculator. What I'm going to do is just plug in our original function. So x squared minus 5x minus 6 over x squared plus x minus 12. And let's zoom out here. And what we'll see is our zeros, -1 and positive, -1 and positive 6, just like we found there. For the vertical asymptotes, if you wanted to, you could graph those. So like at -4 and positive 3. And then you could really see how those are, in fact, the vertical asymptotes there. And then holes will be tricky to see with this. I'll show you an example when we get to one that does, in fact, have holes, but it'll be hard to tell. So, all right, let's do this with another function. So again, I'm going to start by factoring. So r of x is equal to 3 divided by, and I'll factor out x squared, which will, I'll factor out a single x, which will leave me with x squared minus 4, which is a difference of squares. So we'll have 3 divided by x times x plus 2 times x minus 2. Okay, so zeros of the graph. Well, if I'm solving for where the numerator equals 0, I would have 3 equals 0, which is a false statement, and that just tells me that there are no zeros. In terms of holes in the graph, nothing cancels out, so there's also none of those. Not too exciting so far. Vertical asymptote. What we'll do is take that denominator and solve for where that equals 0, which will have a lot of things here. So we have x equals 0, we have x equals -2, we also have x equals positive 2. For the horizontal asymptote, so comparing the degrees, so the numerator has a degree of 0, denominator has a degree of 3. So that denominator is definitely larger degree, so we'll just have y equals 0 for our horizontal asymptote. So let's see what this graph looks like. Seemed like not much was going on, but we definitely have lots of vertical asymptotes. So we're going to have 3 divided by x cubed minus 4x. And we can see we have let me zoom in here. 1, 2, 3 vertical asymptotes. Looks like we're approaching 0 in the long run here, so there's our horizontal asymptote. And then we never cross the x-axis, so we don't have any zeros for our graph. Okay, let's take a look at this one. R of x is equal to 3 factored out, so an x minus 2. And then down here we'll have an x plus 3 times an x minus 2. Okay, so this is one where we're getting a cancellation. I want to be careful here because I'm going to kind of look at both forms, but the simplified form, I would have 3 over x plus 3. And really the behaviors of the graph will be completely the same between these two functions. The only difference is this hole is part of it. So in fact, let's start with that hole. So it's coming from that x minus 2. So that tells me that the hole is occurring at x equals positive 2. And if I want the y coordinate, then what I would do is plug into my simplified form. So r of 2, so I go 3 over 2 plus 3, which is 3/5. So we have a hole at 2 3/5. In terms of zeros, what I'm going to do is use this simplified form. So again, 3 equals 0 is a false statement, so that's just telling me that there are no zeros of this function. Vertical asymptote is just going to occur at that x plus 3. So it's where 0 equals x plus 3, so it's an x equals negative 3. For the horizontal asymptote, you can use either one, but what we'll see is the degree of the denominator is more than the numerator, so this is just a y equals 0. Okay, so let's go ahead, and what we're going to do is graph the original function. So unsimplified, that 3x minus 6 over x squared plus x minus 6. And what I want to do is see, okay, so there's our vertical asymptote out there, horizontal asymptote at 0. The graph doesn't cross the x-axis, so we don't have any zeros. But let's take a look at this hole that's happening at x equals 2. So this is where Desmos isn't showing it clearly, but let's see what happens right there. It's actually undefined. So we're not getting an output there. So if I was graphing, I would actually show it like this, where it was an open circle at that, I'm not going to find it again. There we go. At that point, there would be this open circle where we're undefined. And then if you graphed that simplified form, that 3 over x plus 3, what you'll notice is it actually graphs right on top of our original function. The only difference now is going to be that we are defined at 2. There's our 2 3/5, as it is defined for that function. But in terms of our original function, all the behaviors are the same except for that hole. Okay, one more scenario. Thankfully, this is already factored for us. So all we're going to do is just go through the process of the zeros. So I'm focusing on the numerator. So I'll have an x equals positive 1 and an x equals negative 7. In terms of holes, what I'm going to see here is that we would have this cancellation of x equals positive 1, which actually I want to take away that x equals positive 1 from the zeros because it's actually a hole. So I'm going to have a hole at positive 1, and then in the simplified form, if I plugged in a positive 1, it's going to get messy. 1 plus 3 is 4 times 1 plus 4 is 5. And let's throw that in a calculator. So in the numerator, 2 times 64 over 4 times 5 is 20. So 32/5. Yep. Okay, sorry. Did a quick double check that I had everything right. And from there, let's go ahead with vertical asymptotes. We're looking at the denominator and where that equals 0. So again, we're going to leave out the 1 because that's a hole there. But we will have x equals negative 3 and x equals negative 4. And then for the horizontal asymptote, what I'm going to compare is, and in fact the leading terms, what it would look like is I would have this 2 times x squared up here. So I'd have 2x squared in the numerator over, and in the denominator I would have x times x, so just a 1x squared. So the degrees are the same, so I'm going to have a ratio, and it would be a 2 over 1. So y equals 2. And again, we could graph that and see how all of those properties come through.